Hello guys, so in this video we are going to discuss about the symmetric eigenvalue decomposition. So in our earlier video we discussed about the use of or the application or why do you even need the SVD or EVD. Here we are going to discuss about what is a symmetric eigenvalue decomposition. So for the eigenvalue decomposition, the matrix has to be a square matrix and a symmetric matrix. So that is the requirement. So let A be a real and symmetric matrix n cross n, that is n cross n. Then A according to EVD can be decomposed into Q lambda and Q transpose, where Q is an orthogonal matrix, belongs to a real number of n cross n, suppose n cross n on the real matrix, and since Q is orthogonal, then the Q will satisfy Q transpose Q equal to I, and lambda will be a diagonal matrix that can be written as diag of lambda 1, lambda 2, lambda n, and where we can say that the lambdas are the real eigenvalues of A. Since we have considered A as a real matrix, so if we would have considered A as a complex matrix, then lambda would also be the eigenvalues would have been complex. So eigenvalues, now the question comes that how do we even decompose that matrix? Now we have to prove it that whenever A is a real symmetric matrix, then A can be broken down into Q lambda and Q transpose, right? Where Q is the orthogonal matrix and lambda is the diagonal matrix consisting of all the real eigenvalues in its diagonal element. So let's find out first of all the value of lambdas. The value of lambdas can be found out by taking the square root of the determinant of A minus lambda A equal to 0. So if we take the determinant of A minus lambda I equal to 0, suppose let us take an example here. Let A equal to 2 1 1 2. So A is a symmetric matrix, so we can write A transpose is also 2 1 1 2. Now suppose we take a characteristic matrix Si minus A, then it will be S minus 2 minus 1 minus 1 S minus 2, right? Now if we will take the determinant of Si minus A, then ultimately we will get an equation of S minus 3 S minus 1. So if we equate that equal to 0, then we will get our two eigenvalue as lambda equal to 3 and lambda equal to 2. So our lambda matrix will be with 3 and 1 in its diagonal elements. We got our lambda matrix. Now we can also calculate our Q matrix by finding first of all the corresponding eigenvector for each eigenvalue 3 and 1. So suppose for eigenvalue lambda 1 equal to 3, we can calculate the eigenvector v1 as A minus 3i v1 equal to 0. Then we got our normalized eigenvector as 1 by root 2 1 1. Then secondly, for suppose eigenvalue lambda 2 equal to 1, we got our second eigenvector as 1 by root 2 1 minus 1. Then we got our Q as the combination of the two eigenvector, that is only the Q, right? So Q will be 1 by root 2 1 by root 2 first eigenvector and 1 by root 2 minus 1 by root 2 second eigenvector. So we got our Q matrix. Also there is a property that if we take the determinant of A can also be found out by multiplying all the lambda value. Then we can get the determinant of A. And the trace of the A, trace means the sum of the eigenvalues of A can be found out by summing the eigenvalues of that lambda matrix. So by summing all the eigenvalue, we can find the trace of the A. So next is the spectral norm. So here now in this portion we are discussing about the importance of lambda means the eigenvalues. So using the eigenvalue we can also calculate the spectral norm and the Frobenius norm of the matrix A. So the spectral norm can be found by taking the maximum of all the eigenvalue, then we can directly find the spectral norm. And second, we can also find the Frobenius norm of A by taking the square root of the sum of square of the eigenvalue. So these two are the property. Next we are going to discuss about the positive semi-definite matrix, or also called the positive definite matrices. That is very important in wireless communication. So let A be a matrix, and we considered A belong to set S of dimension n, such that for all the x not equal to 0, we will get, if we get x transpose Ax is greater than 0, then we can say the matrix A as a positive definite matrix, such that for all x not equal to 0, I am repeating, for A belongs to any set S, if for all x not equal to 0, x transpose Ax is greater than 0, then we can say A as a positive definite matrix. And there is also one property, that the minimum eigenvalue of A will also be greater than 0. Then we can say that A is a positive definite matrix and A will belong to the set S plus plus n. Similarly, suppose for all x not equal to 0, if x transpose Ax is greater than equal to 0, not just greater than 0, then we can say that A is a positive definite matrix. So there is a example through which we will discuss. Suppose you can see that here A is 2 1 1 2, A is a matrix. Okay, so for all factors of x not equal to 0, if we calculate, suppose we have calculated the eigenvalues of A, we got lambda 1 equal to 3, lambda 2 equal to 1, both the eigenvalues are greater than 0, also the minimum eigenvalue is greater than 0, then we can also prove it by taking x transpose Ax, or x transpose Ax is greater than 0, then we can say that A is a positive definite matrix. Also, there is one more property of a positive definite matrix or positive semi-definite matrix. Since suppose A is asymmetric matrix and real symmetric matrix, we can break down in using EVD. So obviously, as we have learned, then we can break down it into Q, diagonal of lambda 1 lambda 2 into Q transpose, right? So if we want to take, suppose, the square root of A1 by 2, then we can directly take the square root of the diagonal elements of the lambda matrix. That means then we can directly take the square root of the eigenvalues. So that's all. Thank you.